Hello and welcome to the Exam 2 Solutions Guide. Okay, a lot of good exams, similar spread to last time. Whoops. Yeah, let's get started. Alright, so first, let G and H be groups and let phi be a homomorphism from G to H. Define the kernel of phi. By the way, it looks like there's a bit of a typo here. This and this are the same symbol. It's just like uppercase and lowercase. So he forgot to put the uppercase or whatever, but it's fine. So what is the kernel of phi? I'll just use the uppercase. It's all the things in G that get sent to E, right? That get sent to the identity in H. So let me just write that. It's all the things in G which get sent to the identity in H. You could also call that the pre-image of just the identity. So there you go. So that's the kernel. And then secondly, prove that phi is 1 to 1 if and only if kernel of phi is a trivial subgroup. So we are trying to prove that phi is 1 to 1 if and only if, so this is a bidirectional, kernel of phi is trivial, which means it's only cool, which means it's only the identity of G. Right, so the identity of G always maps to the identity of H. So I know the identity of G is definitely in the kernel of any homomorphism, is always like that. But the question is there anything else in there? And so we're going to say that there's nothing else in there if and only if phi is 1 to 1. So because this is a bidirectional, remember that means you have to prove it in two directions. You have to prove sort of two smaller proofs. That if it's 1 to 1, then it's trivial, and also if it's trivial, then it's 1 to 1. So let's start with this direction. So we'll start by saying, assume phi is 1 to 1. And what does that mean? That means that if phi of x equals phi of y, then x equals y for any two elements x, y in the domain, so in G. So we can start by assuming that that's the case for phi. Well, check it out. We want to show that kernel of phi is trivial, right? So here's the best way to do that, in my opinion. Let G be something in the kernel, right? So I don't know what it is. I'm just saying it's some element of G that's in the kernel. In other words, it gets mapped to E. And of course, we know what else gets mapped to E is E, right? The identity of G always gets mapped to the identity of H. And so we have two different possibility elements of G that are both getting mapped to the same thing. But hang on, phi is injective. Phi is 1 to 1, I should say. Same thing. So we can go straight from there to there. And so look, what did we end up with? We said, well, starting with G being in the kernel, we just deduced that G is actually equal to the identity. So anything that's in the kernel, it's got to be the identity. So the only thing in the kernel is the identity. So the kernel is only the identity. And there's nothing else, because if there was something else, well then blah blah blah, it actually is equal to the identity. So yeah, so that's it. That's the only thing that's there. Okay, now let's go the other way. Assume that, let's go the other direction. So assume that the kernel is trivial. And now here's what we got to prove. We got to prove that if phi of x and phi of y are equal, then x equals y. And x and y in that statement, it has to be the case that x and y could be anything in G. So a lot of people were at this point and made the mistake of saying, let x and y be in the kernel and assume that phi of x equals phi of y. Well, so if you start here, you'd only be talking about phi being injective on the kernel, not phi being injective on all of G. And secondly, of course we know that they're equal on the kernel because they all get sent to the identity. So that's not really what we're trying to get at. We're trying to get on phi being injective on the entire set G. So we can't just say that. We'll say let these be things in anywhere in G such that they have the same image after the homomorphism. Okay, so the trick is to consider xy inverse under phi. Now that might seem like a weird thing to choose, but check it out. We know that phi of xy inverse, right, because of homomorphisms respecting the operation, we can just distribute that over the multiplication like this. And then we can even pull out the inverse as well. And then check it out. What do we know about phi of x and phi of y is that they're equal. So this phi of y, I can replace this with the phi of x. And so that's something times its inverse. And so that's the identity. And of course it's the identity in H because once you've done the phi, now you're over in H, not in G anymore. So yeah, so what is this saying? Well, it's saying that xy inverse get mapped to the identity. And that's what it means for this to be in the kernel. And now's where we get to use our assumption, right? What was the kernel? Well, the kernel was empty. Or I shouldn't say empty, trivial. The kernel had only the identity. So if this thing is in the kernel, well, there's only one thing it can be, because the kernel only has one thing. It must be at the identity. And then finally I'll multiply on the right to get that. So what did that process accomplish? Well, we started with, first we started off with this assumption that the kernel of phi be trivial, but then from there we said, well, if two elements have the same image, then they're actually the same. In other words, phi is injective, or 1-to-1. So there you go. So remember, the two directions are important, right? We did this one where we said starting with it being 1-to-1, the kernel is trivial, and then secondly, starting with the kernel being trivial, D is 1-to-1, right? So you have to go both ways for an if and only if. Okay, that is number one.